So welcome guys. In this tutorial I'll be talking about the control unit. The control unit is the medium between the CPU and the rest of the peripheral circuit. This is actually the block diagram of what the control unit looks like. So I'll be explaining it using the logic sim circuit I have here with me. So this is what the control unit looks like. Just a bit long, but they simplify the circuit to something like this, where these are all the inputs, these are all the outputs. So from here I'll just explain briefly certain things here. One, you notice this set of inputs here, excluding the CPU address. So you notice the RAM data out, bus data in, UART data out, timer data out, IO port data out, and ROM data out. So all these inputs, they are all outputs from different peripherals. So these are outputs from the ROM, output from the IO port, output from the timer, output from the UART, output from the bus, and output from the RAM. So all these are actually sent to the CPU, but before they are sent to the CPU, they need to pass through the control unit. So the control unit actually selects which of them, using sets of multiplexers to know which of them the CPU wants to communicate with. So at the end, after making the choices, the particular data is now saved at the CPU data in. So this CPU data in goes straight to the CPU. So this is the actual data the CPU wants to read. So that is the job of the control unit, to choose between these sets of inputs to know which of them the CPU wants to communicate with, and it does that. So this is the CPU address. Also, I'll explain it briefly. Then again, these outputs here is the RAM chip select, IO port chip select, timer chip select, UART chip select, and bus chip select. Remember, each of these peripheral sub-circuits, they all have their chip select. I already explained all of them. So whenever the chip select is on, that is when they are allowed to receive the CPU data. So the CPU data, the one that comes from the CPU, is not here. We only have the CPU data and the ones that goes into the CPU. So, and they all come from here. But the one that comes from the CPU, they are all they are decentralized. They are all inputs to each of the different peripherals. But before each of the peripheral will process it, it must have its chip select on here. So, and it's also the job of the control unit to select which of these peripherals the CPU wants to read from. So this is basically what the control unit does. It selects which peripheral to send CPU data to and which peripheral to read CPU data from. So I'll briefly explain how this is done. So first of all, we'll notice this set of three comparators. Then this is what they compare. This line is the CPU address. You see the input is coming from the CPU address. This whole line is for the CPU address. Then, but it's not just comparing the CPU address, it's comparing a particular bit in the CPU address here. This is a wire splitter. So let me zoom it in. So you can see here it's comparing bit 5 to 3. So that's the actual signal that goes into these three multiplexers here, and it checks when is equal to 0, when is equal to 1, when is equal to 2. This is when is equal to 2. Then also likewise checks when is greater than 2. So the CPU address bus is 16 bits, but each bit represents is used for a different function. Just as we've seen here, bit this is 0, 1, 2, 3, 4, 5. This bit 5 to 3. So this is the particular bit that is being checked here. Then shortly there, this is another one, bit 15 to 16 goes to this down comparators also. So all these things means that the CPU bus address, each bit goes to a particular part of the bus. Okay, so let me zoom out. Then first of all, the first thing that happens is here. Let's watch this. This particular comparator checks if the CPU address between 15 and 6, 15 to 6 is equal to 0. When that particular bit is equal to 0, when you go to the website, I actually explain each of the bits and what they actually do. But when that particular bit is equal to 0, it's more like a reset. At that point, everything here is off. The CPU is not communicating to anything. So this where it checks if it's equal to 0, the signal comes here and goes through all these multiplexers. So you can see it's first of all went to the AND gate. So for a conditional signal, so then it starts checking again. Now that is when it's checking between 15 and 6. Then it checks between 5 to 3. If it's equal to 0 here, this particular comparator comes here and turns this on, the IO port chip select on. That is, if between 5 to 3 is equal to 0 and this one is 0, therefore this one too will be on. Then this AND gate will be on. Then it will be taking the value of this CPU VMA, and whenever the CPU VMA is equal to 1, it means the CPU wants to communicate with a peripheral. The VMA stands for vector multiple mapped addressing. So whenever it's on, that is when the CPU wants to communicate with any of these peripheral. So if this, remove all this, if this AND gate is on, then the value here will be this CPU VMA. You can actually see that this CPU VMA, let me highlight it, it went into all of this, and also it means whenever any of these AND gates are on, it takes this value. Whenever any of these AND gates is on, it takes the value of the CPU VMA. The same here and here. Else the CPU VMA should select the RAM chip select. So that is how this particular section works. So if none of this option, you should select the RAM chip select. It should be reading from the RAM. Unless there's need to read from the peripheral, then this one comes on and turns either of the IO ports on. So, and one thing about the architecture of this circuit is whenever the CPU is reading, is also writing equally. So that is why these three comparators are used to select either IO port, timer, or UART. So whenever is 0, it represents IO port. If is 1, it represents timer CS. Then if it's 2, it represents UART CS. Then if it's greater than 2, that is this particular signal here, then it comes down and selects the bus CS. So the bus CS, the bus, whenever we're talking about bus, you see a lot of bus CS, bus read write. That bus, they are like an extension in case another peripheral is being added to the whole circuit. So a lot of things were created for the bus. Unlike here, you check for 0, 1, 2. For the bus stands for whenever is above 2. That means it could be 3, 4, 5, 6, depending on how many extra peripherals we are adding to the circuit. So that's what basically the bus is. We've already treated this as individual topics, IO port, timer, and UART, and the RAM also. But this bus represents any other thing you are going to be adding, any other peripheral you'll be adding. So instead of to come and start redrawing the whole circuit to start adding CS, adding chip select for the new peripheral, you just put it to this bus CS. So this is a very good design concept. It means so that in case you want to add more, you can add from here directly instead of reshaping the whole circuit afresh. So that's what this bus does. You see other things like bus count, bus address. So all those things will be going to the new peripheral that will be added instead of redrawing the circuit afresh. So that is why to turn it on, it means whenever is greater than 2. So there's already when is 0, there's when is 1, there's when is 2. Then whenever is greater than 2, so this particular line here goes to the bus. So maybe you're adding a mouse or you're adding a keyboard, all of them will go there. Then again, just like I said, whenever the CPU is reading, is writing. That is why these signals here, when is 0, you can see that it went up and it went down. Then again, let's check this one also. The same thing. When is 1, you can see it went up and it went down. Then the last but not the least, whenever it's 2, you can see also that it went up and it went down. So what they are actually doing is that whenever they are going down to turn any of this on, that is any of these multiplexers on, they are also going up to turn the same multiplexer on up here. So take for instance, let's use the one of 0. So when is 0, it goes up, turns on this multiplexer and selects the IO port data. Then it goes down and turns on this AND gate for this multiplexer and selects the IO port CS. So the IO port CS enables it to send data here. Then this one up here is reading the output data and reading it into the CPU data in. So the same goes for every other, for this one and for this one. So you can see it goes here to select the timer data. That is that data coming from the timer is going to the CPU data in. Then it's going down also and enabling the timer CS to write to the timer. The same for this one, it selects the UART, and down here it enables the UART, it enables the UART CS. So while is reading, is writing. So that is why all these signals are going up and down, up and down, up and down. So another address in the CPU address, the address 0. When you go to the tutorial, I will explain properly and easily what each bit of the CPU address represents. But here, address 0, is used to choose between which part of the RAM output do you want to read. Are you reading the upper 7 bits or are you reading the lower 7 bits? So let's go down more. Let me talk briefly about the rest. So these ones were tied down to 0 permanently. They didn't do anything much. Then you have the board clock. I think I explained this when I was talking about the U out. So okay, I didn't. The board clock is actually the U out clock. I explained it. Yes, I did explain it when I was talking about the U out. From here down uses a different clock. Let me raise this CPU clock up a bit so you see that it's different. Let me raise it up. Yes. So this highlighted circuit here uses this system clock, and it is used to turn on for this register. So this one generates the TS and the RS clock for the U out. Then this one is for the timer. So the U out and the timer uses a separate clock from the system clock. The LED is just a continuous blinker. It just continuously blinks whenever bit 21 turns on. So it's just like when you get an Arduino board that blinks while the program is running. It doesn't just continuously blinks. Probably shows that the circuit is on and working. So this counter is just continuously counting, but particular bits in it, 5 and 6, where I think 5 and 6 was used for the timer, to clock the timer also. Then again, you can see the board clock. I gave the calculation that was used to generate this board clock. There's a calculation behind it. Here is bit 4 is selected, and when you are selecting bit 4, it means you divided by 2, 4, 8, 16 and 30. So this probably divided by 32 counter also. Well, I explained it on the write-up. Then you have the CPU data out also. Here, this is the data coming from the CPU. You can see it goes to the bus also. Just the way it went to each of the different peripherals, it actually went to the bus. So whenever we are bringing extra peripheral, instead of looking for where to get CPU data from, we come here and add it. That is the CPU data out. It goes to the CPU, to the new peripheral that we are adding. So we have also a CPU reset, which is just negating the reset, and this one is active low, this one is active high. So that's just the difference between the reset N and the CPU reset. That means during normal operation we are using the reset N, so it should always be on. If you want to reset, we turn it off because it's active low. So we also have the CPU read write. That one is used to select whether we want to read from the RAM right lower or RAM right upper. We already saw that when I was talking about the RAM. Now what does that is this bit here, and it's coming from the CPU address also. Bit 0 of the CPU address is likewise used to select which part of the RAM do you want to write. Are we writing from bit 0 to 7? Are we writing from bit 15 to 8? When we go to the RAM, we saw how they were used in the RAM. So you can see the CPU read write. So it needs to be off for this thing to work. If it's on, it means it's reading. If it's off, it means it's writing. So whenever the CPU read write is off, and depending on this bit 0, which one it turns on, is going to determine whether we're writing to the RAM lower or the RAM upper. So that's basically all. The RAM address of which part of the RAM we want to write from is likewise coming from the same CPU address. So the CPU address does a lot of things,
I'll break them down on my website. I'll write explicitly what each and everything represents. So let me make this better. I think that is all about this. Next we'll discuss about the CPU. This is externally what they look like. We'll discuss about the CPU on the next tutorial. Thank you.